All right, so today we are going to continue our discussion on modern processor design. But before we start, let's remind ourselves where we are coming from. So previously, before the midterm, we spent a lot of time talking about memory hierarchy. However, after we addressed the issues of the low latency in accessing the memory hierarchy, as you can remember, we pretty much bring down the CPIs that we spend in memory access, including instruction and data, to just a single-digit number of processor cycles. So now, as we mentioned in the very beginning of the quarter, that every time when we have an optimization, we should think about MDOS load again and again. So once we address the memory issue, what's the most significant one that's remaining? And turns out branch is probably the most important problem. So if you look at the frequency of branch, it's probably almost the same as a data memory access, because on average, every 3 to 5 instructions, you are going to see a branch instruction. However, what's the latency of executing a branch instruction if we don't do anything? And the answer is, if it's an Intel processor, it takes 34 cycles. If it's an AMD processor, that probably would also take around like 24 to 30 cycles. And the reason is because if you think about the execution of the branch instruction, it typically relies on a previous arithmetic or logic instruction to generate the input that you use to judge the direction of the next PC. And to determine the next PC, you also need to perform ALU operations to calculate the effective target address in a way that its current program counter of the PC plus the offset from the target instruction to this one. So turns out the latency is pretty much as long as executing the previous instruction. So and if you consider that number of cycles, that's actually more expensive than cache misses nowadays. So the solution that we took in a microprocessor is that we add branch prediction in our processor design. And there are several ways of making predictions. And for example, the predictors that we have learned a lot is called local predictor, which we associate the prediction state together with each branch PC. And we also remember that branch target address in the branch target buffer. And the global predictor also requires a branch target buffer, but we no more associate the state with a branch PC. Instead, we associate the state with a branch history that we have seen before. And based on what's the outcome of the branch history, we train the predictor states separately. However, both mechanisms are not perfect. So that's why at the end of the last lecture, we talk about two common popular hybrid predictors that are intensively used in modern processors. The first one is called tournament. So the idea of tournament predictor is that we have another level of predictor to predict which predictor will give us the vector branch prediction result. So, and that's pretty much like a heuristic-based learning method. And for perceptron, that's more like a neural network-based style predictor in a way that we adjust the weights of that's associated to each bit of the branch history. And based on that weights, it will give us a dot product result. And we use that dot product result. We try to see if we should predict taken or not taken. However, if you think about the basic idea of perceptron is giving different weights or say confidence label to a bit of the global history, then it's pretty much similar to a hybrid predictor in a way that for some of the branches, we probably would trust some of the history bits more. And if all the highly confident bits are from the same branch, then it's pretty much like a local predictor. But if we give like equal weights to all the bits or like similar weights to all the history bits that we have seen before, then that's pretty much like a global predictor. So that's the idea of perceptron predictor is more intelligent choice between global local or somewhat local, somewhat global. So that's why perceptron is also a very popular idea. However, one thing that we have to learn is that no matter what processor you are using, branch predictors, they are everywhere. So when you write your code, you have to be aware there are branch predictors. So that's why it's always the case, if you can sort your data, it will make the branch behavior easier to predict and give us better performance whenever you have a loop or whenever you have an if-else statement. So now, let's go back to this another myth that we have in the programming is that, okay, so a lot of like old school like programmer, they believe the right-hand side is faster, but through our demo, the right-hand side shows no advantages, and in fact, it's going to hurt your performance. So now let's talk about why. And as we chose before, it's because of the data hazard. But let's talk about, so now we are going to dig into the detail of data hazard. So the reason why we did have data hazard is because we have data dependency. If you think about the definition of data hazard, it's the case when I want to execute a later instruction, but that later instruction is still waiting for the input outcome from an earlier instruction, and it's not ready yet. That's why we have the data hazard. So the source of the data hazard is because we have the data dependency. So the data dependency is the likelihood when we are going to have data hazard. So now let's take a look of these pieces of code basically implement the naive version of the swap of two variables. Can you tell how many data dependencies are there? All right, let's take a look. Okay, so most of you picked the answer as B, but why don't you guys talk to others regarding what are the two that you have in mind compare against other people's two? Maybe you will find some difference. All right, what are the two that you guys have in mind? Okay, more of you think it's two, but what are the two? Can someone share your experience with us? What are the two? Any idea? What are the two? Okay. Mm-hmm. The third line depends on the third line, the second line. Mm-hmm. Okay, so the data dependency comes from the fact that a later instruction's input is the output of an earlier instruction, right? So let's check each instruction. So for the first instruction, what's the input? What's the output? What's the input? RDI, what's the output? EAX. So is it any earlier instruction it's waiting for? No. And the same thing for the second, right? But if we look at the third, right, the EDX value is indeed depending on the EDX value of the second. And the fourth one, the EX value is indeed depending on the first instruction. So now let's take a look at this one. So this is actually the S86 translation of the right-hand side. Oops. All right, let's take a look. Okay, apparently for this question, we need some discussion. So go ahead, do it. All right, what do you guys have in mind? So after discussion, more of you think it's 4. So for the first instruction, because it's very first, so we don't expect there is a data dependency it's waiting for, right? But how about the second instruction? What's the input of the second instruction? Okay, so this isn't, okay, so you guys really need to read the S86 assembly handout which has been assigned for reading in the very first reading quizzes, right? So what's an exclusive? So, but even without that information, what's an exclusive OR? What's XOR? It's exclusive OR, right? So what would that instruction do from your perspective? Even though you have no knowledge about x86, what exclusive OR would do? Two inputs, right? So here we have two registers in the argument. So you might be aware, okay, this is exclusive L, right? Exclusive OR. So both of them should be inputs, right? So x86 is an instruction set architecture that's pretty annoying. In several cases, in fact, in its arithmetic operations or memory operations, sometimes the second argument serves as both inputs and output, right? So here, EAX is an input. Is there a data dependency now? With whom? Instruction 1, okay. So now, for the third instruction, any data dependency? Yes. With whom? With 1? Right? So the third instruction, its input is EAX. Who is generating the EAX it wants? Instruction 2, right? Because in instruction 2, we are taking EAX and the content in RSI, doing an exclusive OR, storing the content back to EAX. So at this moment, the EAX of XORL is what I need. So that's a data dependency. How about the fourth instruction? Is it what kind of data dependency it is waiting for? What kind of data dependency does it have? Also instruction 2, right? So instruction 3 is an instruction that simply moves the content of EAX to a memory location. It doesn't modify the EAX. So the EAX of exclusive ORL, the second exclusive ORL, coming from the second line. So how about the fifth instruction? Is it waiting for someone's output? The fifth instruction, the move instruction, what it wants. Which register, which instruction? It's the fourth instruction on EAX, right? Now, for the next exclusive ORL, what are we waiting for? Are we waiting for RDI? We are just, we want to store, yeah, we want to have the value of RDI, right? But typically when we talk about data dependency, we don't count the memory locations in, right? But even with that, we still have EAX as the data dependency. Most of you pick 4, but the answer is actually 5. Now I'm a little bit concerned about your final exam, because this is definitely going to be there, right? So 5 data dependency, 6 instructions, right? So, you know, a lot of programmers, they were proud that, oh, okay, I can use the pointer in this way. But from my perspective, it's like, why are you doing this extra work, right? Because like doing this make your code more difficult to understand, and you have more instruction count, creating more data dependencies. I cannot see any benefit of doing that, right? So like if you are working for a company where your senior engineer keep asking you to write these pieces of a code, leave that company as soon as possible, because I don't think that company is going to make any competitive product in the near future, given they always write code this inefficient. All right, but now, let's take a look of, we say the source of data hazard is from data dependency. And let's see if that really creates a data hazard in our pipeline. So right now, I'm assuming that we have a processor with a relatively complex pipeline in a way that this pipeline is pretty much similar to the latency that we have been experienced in your assignment, in a way that if you could have remember the latency value that you get from your assignment 2, we mentioned that whenever you have an L1 hit, it still takes 5 cycles to execute your instruction. Do you remember that? Right? So that's a standard answer, right? So let's assume each memory access, and we assume this is 100% cache hit rate. Each memory instruction would take 4 cycles. And the same thing for the exclusive OR. Let's assume that the LU operation takes no time, and the exclusive OR also takes 5 cycles in total, right? So what does that mean is that if you have a memory instruction, the first cycle is doing the address calculation, and then 4 cycles to access the memory, and the same thing for exclusive OR. And so let's try to see what's going on in the pipeline. So when we want to draw the pipeline diagram, although there are several ways to draw it, and from my perspective, I would typically do it vertically, because the reason is pretty silly. Most of the time, based on the orientation of our table, we have more space vertically than horizontally. That's the only silly reason why I'm drawing this. Each column represents a pipeline stage. Each row represents what happens in a cycle. So here you can see at the very first cycle, I'm fetching the very first instruction, which I put 1 in instruction fetch. And in the second cycle, I decode the first instruction and fetch the second instruction. So that's why I put 2 in the instruction fetch stage. And everything goes really well. If everything goes really well, right? This is the pipeline that we were expecting. However, this is not possible, because at this moment, this is the 5th cycle. Instruction 3, as we identify, right? We have a data dependency with EDX. However, the generator of EDX, which is instruction 2 at this moment, the EDX value can only be ready after this one, right? After this has been done and we write it back to a register. So there's no way we can have instruction 3 being executed at this moment, right? So the first solution that we have to take is that, again, we have to stall. So now, how many cycles do we have to stall? All right, let's take a look regarding what you guys think. Okay, so a lot of you think the answer is B, some of you think the answer is E. So why don't you guys talk to each other regarding how many cycles do we have to wait? All right, let's take a look regarding what you guys think. Okay, now the answer is more diverse, but like it's shift toward a better direction from my perspective. But why am I saying this? So again, for this kind of a question, I didn't see any of you guys try to use your Apple Pencil or like a real paper pencil, but sometimes just don't be lazy, because the only thing you can do is try to draw a pipeline diagram and then you will figure out why. So let's fast forward to where we have the trouble. So now we are at the 5th cycle, right? And instruction 3 is waiting for the outcome of instruction 2 to come by before it can go to the LU stage. So what does that mean is that before the outcome of like instruction 2 has been propagated to a register, we cannot use it at all. So a stall means that like anything that's including and after instruction 3 has to stay at the same place until instruction 2 propagate its result to a register, which is the write back stage. So, and we remember that, right? Like it's write first and read later. So once it's written, the instruction 3 can immediately get that value. But when we say get that value is still through instruction decode stage. So we have to wait for one more cycle after it's written back. So it turns out at cycle 10, that's the time we can finally start executing instruction 3. So how many empty slots have we created? It's actually 5. So we are experiencing a 5-cycle stall just because of this data dependency, right? So now you know the data dependency really hurts, even though the cache hit rate is 100%, and it seems like, okay, 100% hit rate, what's the problem with that? However, because of the back-to-back data dependency, it requires us to wait for 5 cycles. And this is just like one data dependency we have, right? So some of you might already discover the key why we have to wait for 5 cycles just because we have to wait for the register value to be written back. Then we can start like fetching the value from the register again, then finally put into execution. However, this means that we have to wait for one more step. So a hardware optimization called data forwarding is trying to deal with that in a hardware approach. So to be aligned with what we have, so that's why I have different more pipeline stages here. But for data forwarding, its basic idea is pretty much like, okay, I just create hardware wires that will allow me to directly propagate the result I just created and send it to any potential LUs that would need that value. So for example, the purple here means that's the wire to propagate the result from the memory unit. The green is the one that propagates the results for arithmetic. And for complex arithmetic, we also need the wires. So as you can see here, this proposal is actually pretty expensive in a certain way that it really grows in a cubical relation, well, like a square relationship between the number of LUs, functional units, and the potential target, right? So this is a very expensive to implement mechanism in hardware. However, people like it because in this way, we can save some cycles. So now, if we have this data forwarding, previously we have to wait for 5 cycles, but right now, what does that mean by data forwarding is that we can assume this 2 can directly forward its result to 3 if the next cycle 3 is in execution. So this helps us to save 1 cycle, right? So now we go from 5 cycles to 4 cycles in this case. That's the data forwarding, right? So, okay, if we have data forwarding, let's take a look at this like old-fashioned programmer fabricate pieces of code to see how many places do we still have to stall. All right, let's take a look. Okay, so most of you picked the answer as E, and a lot of you don't think that's E. So why don't you guys do a quick discussion? For those who vote for E, convince others. Maybe you will be convinced as well. All right, let's take a look. So, okay, more of you think the answer is 4. So let's take a look, right? So first of all, the first instruction and the second instruction, because we still have to wait for the first one. So even though we reduce the stall cycles to just 4, we still have to wait for that 4 cycles. And the same thing applied to 2 and 3. And so between 3 and 4, for this set of instruction, because this is just the input, right? So these 2 instructions, they don't have a data dependency. So that's why they can go together. However, between 4 and 5, because again, this 4 is generating the input for instruction 5. So we need another stall. And the same thing between, and so that's why we have, and for the 1, 2, 3. Wait, am I getting it wrong? So in fact, if you look at this set of instructions, right, there are 3 places that we really need to have stall instead of 4, right? Because for this 2, first of all, they don't have data dependency, and once this is resolved, this one automatically resolves its data hazard, right? So that's why 5 and 6 and 4, they don't really create a problem. However, any back-to-back data dependency here, which is 3 pairs of instruction, they all create the stalls. So as you can see previously, the swapping code only have 4 cycle stall, but for this guy, it actually have 12 cycle stalls, right? And if you think about the CPI here is actually 3.17. Like swapping 2 variable here would take 3.17 cycles on average. But previously, the naive version of swap is only 2, right? So that's why this is not very well performing. So stalls and data forwarding can both address the data hazards. However, stalls, it would require equivalent to the amount of memory latency to address it. And data forwarding is not saying better than just save 1 cycle for the write back. And you have to create a hardware logic for that. So both are not a good idea, right? So let's take a look regarding what we can do. So on the software side, if we know that we could have multiple we would like to swap multiple variables, then one thing we could potentially do is that we can, like this one, right? If we know we are going to swapping an array instead of pairwise elements, one thing we can potentially do is that we could do one interesting optimization called loop unrolling. But before that, let's take a look. This is like the traditional version. Like if today what I want to do is to swap contents into arrays, right? So as you can imagine, this is the code that we are going to generate. This is a single iteration, and after the iteration, we are going to jump back. So that's why I have a replication of that. And as you can imagine, right, if I just use the same version as the previously, the next iteration, they will pretty much generate the same behavior as the previous iteration in a way that we always have a 4 cycle stall here every iteration. Agree with that? Right? So that's already the case. We assume that we have 100% hit rate for the branch, 100% hit rate for the cache. And for this 7 instructions, it takes 11 cycles. So the CPI is 1.57, which is still a lot more than 1, right? So now, from the software programmer's perspective, right, can we look into these pieces of code and perform some kind of compiler optimization? All right, let's take a look. Okay, so I like this figure because it means that we need some kind of discussion. So why don't you guys go ahead and do it? All right, so let's take a look. Okay, so after discussion, more of you think it's C. So let's take a look of C, 3 to 5. So can we reorder 5 to somewhere before 3? Can we? Would that give us the right code? Would that give us the right result? If as you guys said, right, if it's C, can I move 5 earlier? Can I move 5 earlier? You guys said that we can reorder 3 and 5, right? What happened if we move 5 earlier? RAX will be incremented by A. What does that mean? Right, so originally you want to move data to the memory address RAX plus RDI. But now, if you do this, that will pretty much be, I'm going to move data from RAX plus RDI plus A, which is not the same location as you want. So this is going to affect the correctness of the code. So this is not an option. So if this is not an option, what's the other one? Right, so if you reorder 1 and 2, right, that doesn't really affect the correctness, but does that help the performance? So if you take a look, right, the answer is it will make the performance better because right now you can remove 1 cycle stall. However, I also hear you guys saying that, why can't I do this earlier, right? So if I am the compiler, if I'm a very aggressive compiler, this is what I would do. I will still do this at Q earlier, but here, don't forget S86 have another field that you can add to a memory instruction code, offset. So here, if I can add an offset saying that it's always minus A to the address that you calculated, then I can get the right result. So here's the thing. You can reorder, but you have to rewrite that instruction as well. Right? So simply reorder doesn't work. You have to reorder and rewrite that instruction. So now, if I flip the order of the first 2 instructions plus rewrite these 2 instructions, right? Then this is what I can do, right? So now, because the first instruction and the second instruction is not depending on each other, so they can keep moving forward. And for the third instruction, because it's simply modifying RAX, so it doesn't rely on R8 or RSI, so it can also be executed. 4 is waiting for R8, and 5 is waiting for RSI. However, it only needs to wait for 2 cycles now, because originally, if it has to wait for 4 cycles from instruction 1, and during this 4 cycle stall, we already fill instruction 2 and instruction 3. And then you can draw the same diagram and you will figure out, wow, originally for each iteration, I have to wait for 4 cycles, but now I only need to wait for 2 cycle stalls, right? So what does that mean is that I can further reduce my CPI to 1.29, which is huge with the compiler optimization. So this technique is called loop unrolling. So in fact, if you want to try loop unrolling by yourself, there are several ways that you can do. So here, I'm demonstrating 3 ways of writing that swap. So the first swapping function is the conventional swapping function. And the second one is I manually add an I++ in between 2 calls of the swap function. And the fourth one is because for the compiler, as we mentioned, it can only do very conservative optimizations. So in case I'm not sure if this is always like a multiply of 4 or multiply of 2, I won't do any unrolling. So here I'm a little bit tricky in a way that, first of all, I divide the size by 4. And then here I multiply the size by 4. So from the compiler's perspective, it will know, okay, you always want it to be something multiplied by 4. So it's safe to unroll this. So if you do this, right, you can check the assembly code that it generates. So from the assembly code that it generates, this is the original loop for the swapping. And this is pretty much the same with the code that we have optimized. However, if we do the unrolling, then as you can imagine, this loop iteration itself has more instructions. But remember, this more instruction itself represents 2 iterations of the original loop. And if you take a look at that, it's actually making like a rearrangement of the instructions, which would further allow us to put more instructions within the stall slots. And finally, for the loop unrolling with this compiler optimization, it actually can unroll the loop by 4 times. So you might wonder, what's the good thing about this compiler optimization called loop unrolling? Because if you take a look of that, right, with loop unrolling, with the optimized code that you guys have seen, right, one thing I could do is I can like put the instructions from 2 different iterations together. And what does that mean is that previously, when I have the stall here, like previously we have the stall here, right? But now with the loop unrolling, I can actually, the first iteration is just for reference, but the second iteration, starting from the second iteration, I can fill the stall cycles from I can use the stall cycles to execute instruction from the next iteration in this stall cycles. So it turns out that at the end, I will not suffer any stalls when I execute this unrolled loop. So that's why here now we can finally get back to CPI equal to 1 with loop unrolling. Because previously you have to stall. But now whenever you have to stall, you can move instructions from the next iteration here for execution. So that's why later on you will see, once you start executing many loops with loop unrolling, you won't suffer any stall cycles. So that's why loop unrolling is helpful. However, as we said, compiler can only do this with 100% for sure that it's always going to be an even number. And the other thing is that for a compiler to reschedule instructions, it's also restricted by how many registers that I can store those temporary values. So there are very limited things that the compilers can do, right? So think about this, right? Can only optimize unstated instructions because I don't know what's the exact loop iterations that you are going to give us. So compiler cannot predict branches, so it has no idea if this is safe to do such an optimization, right? So compiler has limited capability. However, it can help. So now, can we always take advantage of this kind of execution flow without relying on the limitation of the compiler? So here's the thing. If you think about that, from the last lecture, we know the processor has the ability to predict the future, right? It knows if the loop is going to be taken or not, or again or not, through branch prediction, right? So if I have a highly confident branch predictor, why can't I just rely on that to optimize my code internally in the processor? So this comes with the idea of dynamic instruction scheduling, out-of-order execution. So the basic idea of dynamic instruction scheduling comes from the fact that if we remind ourselves, when are we know it's ready to execute an instruction? When you have your data inputs ready, when I know what instructions that you want to do, and when the target ALUs that you want to use are free, right? So as long as these three criteria fulfills, I should be able to execute my instructions. Agree? So what does that mean is that the key thing here is that the data dependency has to be resolved, right? So now let's take a different view of data dependencies in your code. And this method is that we are going to draw a data dependency graph to analyze the code behavior of ours. So this is the this is the unrolled version. This is just like the 2 iteration of the swapping array code that we have just written. And now let's talk about how to draw a data dependency graph. So for the data dependency graph, here's the rule. If there is a later instruction depending on an earlier instruction, let's put an arrow point back to the original instruction. So now for the first instruction, because it's starting, so there shouldn't be any dependency, right? So let's just put it here as a node. For the second instruction, should it have any node with others? Like any arrow with others for the second instruction? No, right? Because there's no data dependency. So let's also put it here. How about the third instruction? Depends on the second instruction. Okay, so let's put an arrow here, right? How about the fourth? Depend on first. How about the fifth? No, okay. How about the sixth? The sixth instruction is depending on fifth instruction. How about the seventh? Instruction 6. Okay, so you might say, well, why is it depending on instruction 6? But that's the convention of x86. So it has to, so any branch instruction following a comparison instruction is consuming the flag produced by that instruction. So there is an implicit data dependency here. Now, how about instruction 8? Who is it depending on? 7? 1? What are the inputs of instruction 8? 3? Okay. Okay, so RDI, that's the input, right? Anyone changing RDI? No. RAX, anyone changing RAX? Fifth instruction, right? So 5. How about instruction 9? Which instruction? Also instruction 5. How about instruction 10? Instruction 9, right? How about instruction 12? 11? 8? How about instruction 12? Instruction 12? 9? Why is it 9? None? Where do I get this RAX value from to increment? 5. Okay. How about 13? 12? How about 14? 13. Okay. So look at this data dependency graph, right? It looks like we actually have 3 different streams of instructions that we can execute, right? Like instruction 1 and 4, instruction 2 and 3, and for this part, right? And for the rest of these 3 streams, as long as 5 is resolved, they should all can go away in parallel, right? That's what we can do in theory. Agree? That's what we can do in theory. But in practice, how many of this can we really reorder? All right, let's take a look. Okay. Oops. What happened? Okay, let's take a look. Okay, so looks like most of you agree the answer is the first pair. So let's take a look, right? So if we reorder the first pair, right, as many of you already identified, it doesn't really affect the performance. It's pretty similar to what happened before, right? But let's take a look. Why are we not able to reorder 3 and 5? Because if you look at the data dependency graph, right, there is no relationship between 3 and 5. So what's wrong with 3 and 5? What happened if we reorder 3 and 5? What would get wrong? It still changes the RAX, right? Because they because the later one, it wants to output to RAX. Okay, how about 4 and 6? They also don't have any data dependencies, right? But what happens if I try to reorder 4 and 6? So if I try to reorder 4 and 6, right? For the 6, it won't get the right RAX. For the 4, it will also not get the right RAX, right? So it's all because of the problematic RAX. How about 6 and 8? Right? 6 and 8, they are in parallel. Can we reorder them? So the answer is yes, if the branch prediction is perfect, right? So 6 and 8 is also a viable answer. How about 3 and 8? How about 3 and 8? Did 3 and 8? How about 3 and 8?
No, because RDI,
Because RAX, right, is also wrong, right? So as you can hear, the reason why there's only very limited number of pairs that we can reorder, even though they don't really like to have, they really don't seem to have data dependency in a graph, is because, like, we keep hearing because of RAX, because of RAX. And the reason is because they have this, they are either fall into this one of this situation. The first situation is called write after read. It means that a later instruction is trying to overwrite of the source of an earlier instruction, right? Like we say, if we reorder this one, it would overwrite the RAX, which is the input of many instructions, right? So that's why we cannot reorder. And the other case, why we cannot reorder is called write after write. It means that a later instruction is trying to overwrite an output of an earlier instruction. So if you try to do that, the outcome of an earlier instruction is going to be vanished. And your code will also be incorrect, right? So if you hear the sentence here, right? If you hear the sentence here, all the problem comes from the fact that a later instruction overrides the input or output of an earlier instruction, right? So what does that mean? If I want to reorder freely, what's the key here? Right? So if the problem here is that it will create an issue of overwrite an earlier instructions, either source or destination, what's the best way to deal with that? What do you think that's the best way to deal with that? So here's the solution. So here's the way. What if we can give each new output? So for example, the later instruction, we can redirect its output to somewhere else than RAX. Or in general, the input or output of an earlier instruction. Would that solve this problem? Would that solve this problem, right? So let's take a look, right? So now, if we can have more registers, which means that now I am rewriting all the output registers of an instruction to a temporary registers, for example, right? What would that be? So if you take a look, for this instruction, let's rewrite this RSI to T0, RA to T1. So now, instruction 3 and 4, they are depending on T1 and T0. And for instruction 5, originally it's depending on RAX and store value to RAX. Now, let me extend it and make it store to T2, right? And then the instruction 6 is now depending on T2. There's no RX anymore. Agree? Right? So anything that's related to the RX issue is now gone. And for instruction A, because the RX is indeed coming from here instead of the original RX, so it should be rewritten to T2, right? So the original issue here that was involved in RX, they are all gone, right? So if you pay attention to this philosophy, take a look at this rewritten code. All the false dependencies that we have mentioned, they are all gone, right? So you can imagine if we really want to achieve out-of-order execution in hardware, here's the key. First of all, we need to do register renaming in a way that we want to rename the output register to somewhere else. And the second thing is that because, as we mentioned, the key thing to continuously executing is that we have to execute instruction that has been predicted. So executing instruction that is on the path of predicted branch is called speculative execution. So these are the two main things that we have to support in hardware. So to support this, here is the solution. So for the register renaming, hardware will redirect the output register from their original architectural naming to a physical register. And which means that now, in a hardware, you need to maintain a mapping table between the latest up-to-date architectural register, which is like RAX, RCX, RBX, to a set of physical registers that really stores the value, for example, T0, T2, right? And then for the out-of-order execution engine, you just need to check if any instruction has all their operands ready and issue those instructions to the corresponding LU or functional units when it's free. So that's the whole idea of out-of-order execution, right? However, there are several cases that we might get it wrong. So for example, branch prediction is still prediction. It's never going to be 100%. And sometimes in your code, you may have exceptions, for example, page fault, for example, sec fault, for example, divided by 0. So all this situation will cause our predicted set of instruction to be wrong. So in your hardware, you also need to temporarily buffer the result and preserve the capability to recover it. So that pieces of hardware is called reorder buffer, which means that at the end, I also need a circular queue to maintain the order of my instructions during the instruction before I can safely discard its temporary speculative state. So now, in your processor pipeline, it would be a little bit complicated in a way is that whenever you generate a result, your instruction result is currently put in reorder buffer. And only if that result is 100% for sure should be seen by the programmer, we consider to commit or say retire that instruction. So you can imagine in your pipeline, it's now getting more complicated in a way that it's not just when you decode the instruction, in the meantime, you already know how should I rewrite its output. So this is called register renaming. And once you rename the instruction, you allocate a buffer location in a circular queue to store the temporary result for that renamed instruction. And whenever it's ready to issue, your reorder buffer logic would release that instruction to any of these functional units to execute. So that's the new pipeline that we have. So for this pipeline, let's take a look. How am I going to execute this set of instructions? So first of all, for the first few instructions, I would definitely be able to put them in consecutive pipeline stage without any stalls. Now, they're starting. So now we assume the first instruction is in renaming stage. As we previously mentioned, during the renaming stage, what we want to do is that we have to allocate a physical register for its destination. So the destination here is RSI. So now I'm allocating a physical register that's called P1 for it. And in my hardware, I would say, well, the value of P1 is not valid yet because it's not being generated, but it's in use. So don't allocate it for somebody else. Now, after I rename this, I'm ready to put this instruction in execution, and now I can rename the second instruction. So here, as you remember, we have multiple pipelines, which includes address generation, LOU, MUL, and BR. In the modified issue logic, at this point, I'm only allowed one instruction to be put into execution. So what does that mean is that only one of them can have an instruction at the same cycle. So at the next cycle, I'm trying to rename instruction 2. And instruction 2, it has a destination of R8. So I have to rename it, right? So now P2 is not in use. So definitely I want to rename it to P2 before I can put this instruction into execution, right? Now, instruction 3, it doesn't have an output. However, its input is coming from P2. So I also have to rewrite this instruction in a way that, or I need to remind myself this instruction currently don't have the P2 value that is ready. And instruction 4 as well, I also know that it's not ready yet. So both of them, because their inputs are not ready yet, so I can only put them in a renaming stage at this moment, and it's not ready to be issued. And now for instruction 5, it's generating a new output. So at this moment, I want to rename instruction 5. And I want to rename its output. So for the RAX value, now I have a new value for it. That's actually P3, right? And if you look at this instruction, because I am not really relying on P1 or P2 anymore, right? It used to be I cannot put this instruction into execution because other instruction, like instruction 3 and 4, are still relying on RAX, right? But at this moment, because I'm just modifying P3, so it's very safe that I can execute instruction 5. So the next cycle, previously, you have to wait. But now, I can execute instruction 5. So this is an evidence that this pipeline would help us to execute instructions out of order. And in the meantime, I am receiving instruction 6. So let's take a look at instruction 6. It's comparing the value of RAX and R9. And the RAX is coming from P3. So if you look at the next cycle, who generates P3? It's actually instruction 5, right? So the next cycle, this value will be ready. So the next cycle is very safe that you can put instruction 6 into execution. However, we chose not to do that for a reason, because at this moment, instruction 4, who also, depending on the value of P1, is ready to be executed. So we put 4 because it's an earlier instruction, so it has higher priority. And the same thing is that you can imagine the next cycle, instruction 3 will also be executed because its depending value is already arrived. And in the 11th cycle, we can finally put instruction 6 into LU stage. And in the meantime, concurrently executing instruction 3 and 4. So if you go forward to this pipeline diagram, you will figure out its efficiency is actually pretty good in a way that you can see, well, although I do have some slots wasted for the address generation, but almost every cycle, I'm putting a new instruction into execution later on, right? So if you check the throughput, right? If you check the throughput at the end, you will figure out that after the first iteration, I'm pretty much executing 7 instructions in 7 cycles, which is CPI equal to 1, the best CPI that we can achieve. And with this pieces of code, we haven't made any compiler optimization yet. We didn't make any compiler optimization yet, right? So in fact, this is very interesting in a way that if we go back to the demo that I showed you earlier today, if we go back to the demo that I showed you earlier today, if I run the generated code, and let's take a look of the performance of each of them. So if you take a look, right, the manual on road, okay, so if you run it several times, you'll figure out that the performance between these 3 versions of code, they are actually pretty minimal, especially the first version and the second version. The first version, remember, we didn't do any unroll. The second version, I manually unroll. And the fourth version, it's aggressively unroll, right? And you can see the first and the second version, there's almost no difference. And the reason is because the processor itself already do this aggressive internal out-of-order scheduling, which make a limited degree of loop unrolling becomes less useful than the past, right? So this is something interesting to discover. And in the next lecture, we are going to talk more about this out-of-order execution because that's actually the basics of processor execution nowadays. So pay attention, spend some time reading the slides today, going through those pipeline diagram, pipeline timing. And before you leave the classroom, don't forget assignment 3 due this Sunday. And I only see 2 of you, well, only 1 of you submitted the programming assignment for 142L. So I just want to warn you, the programming assignment 2 is not as easy as you can imagine. And if you didn't submit, I won't allow you to continue. So pay attention to the programming assignment 2 as well if you are in the lab. And there's no lab lecture for today. Next Monday, I won't be around, so no lecture. I'll use that time as a slack. Reading quiz 7 due next Wednesday before the lecture. Other than that, enjoy the rest of the day. I will see you next Tuesday.